All right, guys, so this is the first part of the lab, part A. I'm not going to go through all the connections because that's impossible to explain and nobody would follow me. So all it is I'm supplying three loads in parallel. We have the resistor, inductor, and a capacitor in parallel. Each one is 300 ohms, being supplied by 60 volts. I set that with the variable power supply, and then I'm setting up my data acquisition interface so that I can measure the voltage across the load and the current being supplied by the power supply. Okay, and that's pretty much it. Right now, the switches for the loads are open, so the loads are not connected. So right now we just have kind of an open circuit. But anyways, I have all the connections open. I have over here on the computer that is receiving data from the data acquisition module through the USB there. I have my windows open in the LV EMTS software. So we have the meter window here, which acts like a multimeter. And so I can display my AC voltage, current, and power. This is real power being consumed right now. I have an oscilloscope window for showing the voltage waveform and the current waveform. You can see that the voltage waveform is there because I have 60 volts set, but the current waveform, which is yellow, is still pretty much at zero because we're having an open circuit right now. And then this is the phasor window, and this will allow us to see the phase difference between voltage and current, and that's what it's most useful for. Actually, I'm going to adjust the voltage phasor so it's 50 volts per division, so you can see it a little more there. But anyways, once the current waveform comes up, you'll see a yellow waveform on top, or sorry, I should say pink one on top. Okay, so with all that set up, the first part of the lab is to close the switch for the 300 ohm load, so that now we have a 300 ohm load across resistive load across the power supply. And if we go back to our windows, we will see that first of all there's current now, about 0.2 amps of current. And if you think about it, it makes sense. 60 volts divided by 300 ohms should give 200 milliamps, which is what's shown here. And then we also have our oscilloscope window. See that the voltage and current waveforms are in phase with each other. Okay, and that's the most important thing to see from this, that they're in phase with each other. And finally, you can also see that they're in phase with each other through this phasor analyzer window. You can see this is the voltage waveform, and the current one is extended a little farther out because we have it at 0.1 amps per division. So anyways, that's with the resistive load connected, and that makes sense. Resistive loads should have their voltage and current in phase. The power factor would be 1 here. And we can also see the real power consumed is 11 watts. Okay. Now I'm gonna close the switch for the resistive load and do just the inductive load on. And now observe. First of all, look at the waveforms here. Actually, let me say, it's still about 0.2 amps of current. Maybe it's a little less because there's resistance associated with the inductor. And you can see that there is real power being consumed, even though we know that if it's a pure inductor, a purely reactive component, there should be zero real power. But anyways, about 0.2 amps of current. You can also see that the waveforms are now not in phase with each other anymore. Observe the current waveform is yellow, and the green waveform is the current waveform is yellow. The green waveform is the voltage, and look, the voltage is it's ahead. This looks like the waveform is behind yellow, but because this is time, you can see that the voltage waveform has reached its peak before the current one. So you can see that the voltage leads the current waveform, and this is more easily expressed over here. This is the voltage waveform, and this is the current one. A purely inductive load, we should expect that they should be 90 degrees out of phase, voltage and current, and the voltage should lead. And indeed, that is almost the case here. We have an 82-degree phase difference, and the current lags the voltage waveform by 82 degrees, which means that there's about 8 degrees, you could say, of 8 degrees to go, which is probably being, this disparity between an ideal case and this actual case we have here is probably put about because of the resistive component of the inductive load. But okay, so that's with the inductive load. Now I'm going to do the capacitive load, and there's actually going to be something interesting. So what we expect is the capacitive load will be opposite the inductive. Current will lead voltage, but everything else is, about the same as what we saw. But look at this now. If I turn it on, I'm just going to show the meter window first. So again, about 0.2 amps. In fact, this is almost very close to ideal here 60 volts over the 300 ohms, minus J 300 ohms, you could say, of reactive impedance gives 0.2 amps. There's very little real power being consumed, which makes sense. A capacitor would probably have less, you could say, parasitic resistance than an inductor. So indeed, there's very little real power consumed. But what I think is interesting, and actually I'll go down a little bit to show you this over here. The phasor diagram does indeed show us an almost ideal capacitor. We have 90.9 degree phase difference between the voltage and the current waveforms. And indeed, the current waveform, which is this, is ahead, 90 degrees ahead of the voltage waveform. So voltage lags current, and this is a capacitive load. That makes sense. But now look at the oscilloscope. So, dear God, yeah, what is that? What is this yellow waveform? First of all, imagine just the fundamental harmonic over here. So again, this is the voltage waveform. This is the current one. You can see now the current reaches its peak before the voltage. So we can see that 90-degree phase difference is indeed the case here between the voltage and the current, which we expect with a capacitive load. But there's also a ton of other harmonics involved here. And so that does seem a little strange, a little weird. And actually, that was not something I expected. Well, I did this lab 2 semesters ago at least, so I saw it for this then. But when I did this lab for the first time, I did not expect this. And the best answer I can come up to explain as to why there are all these other harmonics is perhaps these, this capacitive load, the capacitor we're using, we pulled it out and we saw that it was a power film capacitor with an oil dielectric. And so depending on the properties of that dielectric, that oil, if it was very nonlinear in the operating range that we're doing it at, so if at 60 volts, it's very nonlinear, then you will see a lot of added harmonics, okay? And by nonlinearity, maybe, I'm not sure if you guys took it yet, but if you guys took transformers and you observed saturation, that hysteresis curve for a core, a magnetic core, well, dielectrics have the same thing, except instead of, magnetic fields, we're looking at electric fields. And so they also have this kind of curve. If you're operating in that linear region, then you'll have, a nice sinusoidal waveform. But if you're operating in that saturated region of the hysteresis curve, you'll find indeed that you'll get these nonlinearities, these added harmonics on top. And I'm gonna hypothesize real quick, and I actually haven't tested this. If I lower the voltage, the nonlinearity should go down to the extent that we maybe can see a purely sinusoidal waveform. So I'm going to test that out real quick to see if that works. So let it update slowly. You can see the voltage going down on the right there. Wow, no, it doesn't seem like it's going away. Yeah. Not really. As in the same proportion of harmonics is still there. Very clearly. Let's see how far. Let me go down to like 10 volts and see if that kills any harmonics. I'm gonna increase the vertical scale. Yeah, no, I think the same proportion of harmonic. Maybe it's a little less. But yeah, that seems weird. So I don't know if it's quite that. That's my best guess. I remember I did look this up online a while ago and I did not get necessarily a straightforward answer. Maybe I could look into it more. But anyways, in case you're wondering, what is this really strange waveform? Hopefully now you see that, okay? The last part of part A is where you have all the loads connected at once, okay? So the resistive load and the inductive load I'll put in. Now what should happen is the resistive load, it'll remain as is, but the inductive and capacitive and inductive loads, they have equal and opposite admittances, and they are in parallel. And so their admittances together, summed together, will add to zero admittance, which means no current will actually run through them from the power supply. So there'll be an open circuit. So what you'll find is that the current, is that the waveform should appear as if we just had the resistive load connected. Even though we do indeed have a capacitive and inductive load connected in parallel as well, it will appear as if we just have the resistive load. And if we go ahead and look at that, that's not quite the case, okay? Because of the harmonics that we saw with the capacitive load, we don't get that perfect canceling out. The current waveform should be a little more clean, first of all. But what you should notice, and this is the main cancellation that occurs, is that indeed, look, the current and voltage waveforms are almost in phase with each other. And you can also see that here the peaks line up almost exactly because of that equal and opposite admittance that the inductor and the capacitor provide the circuit. So anyways, that's part A. I hope I didn't miss anything, but yeah, all right. All right, guys, this is part B of the lab. So I'm definitely not gonna go through all this wiring, but anyways, I built the circuit that was shown in the diagram, which is there. Ignore the part C part. That's not a mistake, but this was last semester's lab. I made it for part C, but I changed it this semester. Anyways, I just built the circuit over there, and with that, this more complicated load, that's the point of this. You can see for this more complicated load, we have about 83 milliamp being drawn, about 4.5 watts of real power. And let me actually do something real quick. I did not put this in the lab to do, but I'm gonna do it anyways. You can see that. Okay, let it update. Oh, it's E2I2. Yeah, let's change this real quick. Never mind. 1 second. Here we go. I'm just gonna show that it's drawing reactive power as well. Okay, so I1 Q. Okay. All right. There we go. So it's drawing about -2 VARs of reactive power, which means that it's a net capacitive load, by the way. And we see here this is the real power being drawn out of the load. And you can see the waveforms. Again, the green one is the voltage waveform. This is the current. You can see the current leads the voltage waveform by a little bit. And you can also see here more clearly in the phasor diagram, this is the current waveform, this is the voltage waveform. Observe the current leads by a little bit, and that amount is about 24.6 degrees in phase. Okay, so that is the current situation. So we have a complicated load. So that's the first part of this part of the lab. And then I say correct the power factor. As in correct this entire load, place something in parallel over here to correct everything afterwards so that the voltage and current waveforms are in phase. We have a power factor of 1, and we have almost 0 reactive power draw. And that's what you would go back to the background and information section where I walk you through steps for how you correct for a power factor. But I've done the calculations. I did it on the board over there, and I have my corrective load over here. Now, I should have had some more hindsight to remember that the actual load is not available because all the terminals are used up. But anyways, I just took one of the modules out and connected it up, and so I have a corrective load. You can see it's inductive, which kind of makes sense because the load is net capacitive, so you need an inductive load to correct its power factor. And I set it up, and I've done everything. And once I turn the needed amount, the needed impedance, you can see if I go back here, right away, you can see everything seems to be corrected. The real power is about the same. Maybe it's a little more because the inductive load has some resistance, so it consumes some real power. But look at this. The reactive power draw went from -2 to almost 0 at this point. So it's dropped drastically. We still have about the same amount of current. Actually, no, a little less current, which makes sense. That's one of the features of power factor correction. You reduce the current requirements from your power source. And look over here, the voltage and current waveforms are pretty much in phase. And you can also see that almost exactly in phase, just 0.9, 1.3 degrees off from each other, but that's, almost exact. So that's very nice. In fact, I can show you dynamically what happens if I switch everything off, the corrective load off. There, they become offset. If I switch it back on to correct the power factor, let me also show there. Then there you go. You can see they correct themselves. So that's power factor correction live in action from Fargo, North Dakota. I'm kidding. Okay. Anyways, that's part 2 of the lab. Okay, guys, finally, this is part C of the lab. And this is where we finally build a 3-phase circuit, which is what you guys have been learning all about in class. And it's the world of power systems, 3-phase circuit. So, okay, all it is here is the simplest kind of 3-phase circuit. We're now using all of our terminals in the variable voltage supply. We set it that against 60 volts like we have been. And we just have 3 resistive loads on each, you could say on each line, 300 ohms on each line. And so because the loads are balanced, we should find that the currents should indeed be three-phase, and the voltages are three-phase by default. That's what's coming from the building's power system. So if we go ahead and look at the scope and the phasor diagram, you can see here the scope. I'm showing the voltages first of all, and indeed they are three-phase. That looks pretty classic, three-phase type of waveforms, and these are the voltages. I also have on the phasor diagram the same thing. You can see the 120 degrees out of phase with each other, and I also drew the longer lines. You see, this is a light red line. This is a dark red line. The darker lines are the currents, and because the loads are balanced, the currents are also three-phase, which is an important note to keep in mind. Currents are not necessarily three-phase just because the voltages are. The voltages will be three-phase because that's the nature of the generation of that power. When you learn about generators, you'll see how three-phase voltage sources are generated. So the voltage will usually be three-phase, but the currents are not necessarily that, because the currents will depend on whatever load is attached to each line. So here we have resistive loads, and so indeed we see that three-phase nature. Resistive loads, and they're all equal, so we see that three-phase. And also because they're resistive, as you should have learned from the lab so far, because they're resistive loads, the voltage and current are in phase with each other. Okay, so that's that. Also, one last thing I'll note is you can see the ABC sequence over here with the voltages. This is A, and then minus 120 degrees. This is the second voltage source, and then minus 240, which is the same as plus 120. And so that's kind of the, I believe, if I'm remembering this right, this is the positive ABC sequence. Okay. All right. Okay. And then the second part of the lab has us, let me remember here. Okay. Yeah. The second part of the lab basically has us. Okay. Now that we've seen and we've confirmed that everything is three-phase, let's go ahead and show what the difference between line to neutral and line to line is. So all I'm going to do is I'm going to first turn the knob to 0, turn off my power supply. I'm going to remove E3, which is over here, because that's not important anymore. So let's try and do that. Well, anyways, it's disconnected. Let me just set it aside. You can see why I don't show you the wiring, because it takes forever. But anyways, okay, now that I have disconnected E3, what I'm going to do is switch out whatever E2 is measuring. E2 is currently measuring the 5 to N, so the 5 to N line to neutral voltage. I'm going to switch that to measure the 4 to 5 line to line voltage. Okay, so I'm going to go ahead and do that right now. So let me check this real quick here. It's going there. This one is following through here. Okay, so that's where, oh, that's the neutral. So yeah, I'm going to go ahead and do that. This is 5. Okay, and this is measuring that. I'm going to go ahead and switch that here. Okay, I've switched it up. I'm going to turn this back on and set it to 60 volts once more. I'm going to remove the unnecessary waveforms. I don't care about those. All I care about is E1 and E2. And I'm also going to do the same here. I'll show that there. So look now. Okay, here we have the green is the line to neutral voltage. Okay, and the yellow is line to line voltage. So green is 4 to N, that A voltage, let's say, between it and neutral, the line to neutral voltage. It's 60 volts. And then you can see this line to line, which is between 4 and 5. So kind of the AB line to line voltage. You can see, first of all, it's higher in magnitude. And you should remember from class, this is square root of 3 times higher. And you can also see that it is leading the line to neutral voltage by 30 degrees. Same thing here, you can see in the phasor diagram, this is the line to line voltage. This is the line to neutral voltage. You can see about a 30 degree phase difference, and the line to line leads the line to neutral. And it's larger by a factor of square root of 3. Okay, so that's showing that part. Now for the next part of the lab, I'm gonna have to pause this video because I'm gonna have to rewire stuff. What I'm gonna do next is switch the load from being a Y configured load. I should have mentioned that first. This is a Y configured load. I'm going to switch that to a delta configured load while making sure the currents are the same. So, yep. Okay, give me a second now. Okay, so I'm going to film this rewiring. I had it initially connected as a Y configured load. I'm going to film how you do it into a delta load because it's actually a little bit hard to visualize how you connect a delta configured load. I remember the previous semesters, people had a lot of trouble doing that. So I'm going to go ahead. I'm just going to switch those off. And the power supply is off and everything. I'm going to show you how you do that. Okay, the way I visualize it is, okay, here's my 4 to N, 5 to N, and 6 to N line to neutral voltages. Okay, so that's what I'm getting the power out of. So, okay, first of all, you go from the 4 to N, it goes to the first load. And then, okay, this first load connects back to the 5, connects back to the next load in series, in a way in series, okay? So I'm gonna go ahead and do that. So 4 goes to 5, and then 5, that's how I think about it. 5 goes to 6, the next load, also like as if they're in series, and then 6 goes back to 4, like so, and that's it. That's your delta configured load. Okay, it's as if you just have 3 loads in series, kind of in a circle. All right, and then you're gonna connect your power supply, your powers to each of the top terminals. Okay, and that's pretty much it. I'm gonna go ahead and do that right now, real quick. So you can imagine this is the 4 terminal, this is the 5 terminal, and this is the 6 terminal. And if you want, you can go ahead and draw a delta configured load, draw your 3-phase power, and see if what I just said makes sense. And hopefully it does. Hopefully I wired this up correctly. And if I did, you'll find, look, there's this neutral line that used to be there with the Y configured load. I can remove that now because delta configured loads do not have a neutral line. Okay, so actually there is a benefit to delta systems. Just on this basis, they require less wires. Okay, and you'll see that there's actually other benefits from delta configured loads. Some of you might not feel like there is much of a benefit, and they're a little bit more complicated and weird to analyze. But trust me, there are benefits. For example, 3-phase transformers, when configured delta-wise, there is a benefit to that because that delta configuration, for some reason, will help eliminate harmonics. But anyways, that's for future labs. But just know that delta configured loads do have their place in the world. And here's just an example of that. And also, this is something that you should calculate. But I'm going to go ahead and see what the equivalent impedance is. And remember, the point of this was to switch to a delta configured load while making sure that the currents remain the same. So it's as if the load has not changed from the perspective of the generator. So the generator is still doing its 60 volt thing, supplying the same amount of current, but the load has just switched to a delta load. So the generator can't tell the difference, but you just change it. And that's just a way of you practicing how you can change a load between Y and delta without affecting the rest of the power system. Okay, so I'm going to go ahead and test that out. I'll just pause the video for a second. All right, so I have the computer configured. It's measuring the currents going through. I removed all the voltage measurements because we don't need that anymore. So I'm just measuring the current going into the load. If this is, first of all, if this is correctly put up, we should see, 1, that the currents are 3-phase, as in equal magnitude, 120 degrees apart. And 2, we should see that the same magnitude of current is going into the load as well. And if we go ahead and look at our oscilloscope, indeed, it does appear 3-phase. So that's good. And also, if you remember, the magnitude was about a little over 0.2 amps for the Y configured, and indeed, it's about the same here as well. On the phasor analyzer, I don't know why these are shifting around so much. They should remain still relative to each other, and you kind of see that here. If you see the waveforms, they look pretty stationary, at least relative to each other, but this over here is kind of going wild, and I'm not quite sure why. But anyways, we have our 3-phase delta configured load converted from a Y configured one. So yep, that was that part of the lab. I'm going to pause again one more time to get to the last part of the lab, which is to show the neutral line. Guys, this is the final part of the lab. I returned everything back to a Y configuration on the load side. And so all this part is to show you what happens to the neutral line and why it's there when you have a Y configured load. Okay. Now, ideally, if you had a perfectly balanced load and a perfectly 3-phase voltage source connected to that load, then you would have no need for a neutral line. Okay. And you will see here just exactly that case. So I have the Y configured load here, and I'm measuring the current through the neutral line, and that's I3. This is the current through the neutral line. This is the current through any one of the loads. Observe, we have 300 milliamps through any of the loads, RMS obviously, and we have about 12 milliamps in comparison going through the neutral line. So it should ideally be 0, but you can see that it's very close to 0, especially when compared to the actual currents moving through the loads. And that's what you have when you have a balanced load. That neutral line, because it has so little current, it can be made much thinner, or it has less strict requirements on it because it doesn't have to carry as much current, assuming that the load is balanced. Okay, and now to show you what happens when the load becomes unbalanced. So I have 200 ohm loads here with 60 volts, which is why you can see 300 milliamps. That makes sense. I'm just going to change any one of these loads. Let me change this to be a 600 ohm load, so it takes a lot less current. Well, guess what? That current has to go elsewhere. So if I do that, I made the switch. You can see now, look at the difference. First of all, it's taking a whole lot less current. And look at the neutral line. Now the neutral line is really taking a lot more current. And that's what happens when the load becomes unbalanced. When your three-phase Y-configured load becomes unbalanced, the neutral line starts to take a whole lot more current. Okay? And I also want to show you actually one more thing. So I'm going to return that back to being a balanced three-phase load. I actually want to show you the waveforms. Because I said before that even if the voltage source is three-phase, the currents may not necessarily be three-phase. So I'm just going to switch one thing here real quick. I'm going to pause the video. Okay, so I changed, I just made it so that now I can measure I1, I2, and I3. And you can see here, the three waveforms are indeed three-phase, and I have the load balanced again. So they're three-phase. If I change now, just like I did before, if I change one of the loads, so it now becomes an unbalanced load, observe the waveforms. Look at that. First of all, no longer three-phase. Clearly, you can see I guess it's hard to tell, but you can see this phase difference is a little less, is smaller than the phase difference between here and here, these two peaks. So the phases are no longer 120 degrees apart. Also, the magnitudes are not the same anymore. This is a lot smaller than these, and those two things violate the requirement to call something three-phase. You can see the phasor diagram is going absolutely bonkers. It's just all over the place. But yeah, anyway, so that's just what happens when you have an unbalanced load. So there we go. That concludes the lab. I know this was a lot, but hopefully this gave you a very thorough introduction to the lab volt electromechanical training system, and it also applied everything you learned in the beginning of this class. Okay? All the best. Thank you.